Alright guys, let's do some fun. Today we're going to talk about a lot of people, we went over this in class on Friday for the afternoon classes. If you're in the morning, this may not be something you've had before. But here we go, we've got a weight. Let's say it's going to be, I'm going to get something unique. It's going to be 2.5 kg mass. And this mass is hooked to a point right here. Let's call that point A. It's hooked to point A, and extending from point A are two ropes that connect to maybe the ceiling or some hooks on the wall. So these are ropes. And this is a weight hanging from the center of these two ropes. Alright, well, what's going on here? Well, we assume that this whole thing, this whole area here is stationary, and that's going to tell us something extremely, extremely important. Once again, if anything is stationary, it's going to be at equilibrium. Now, you should know that equilibrium, F net, which is the sum of all the forces, equals 0. But we can even be more specific with this, guys, with two more rules. We can say F net in the x direction, very important, which is the sum of all the forces in the x direction, will equal 0. And then we can say F net y, which is the sum of all the forces in the y direction, is also equal to 0. And these are newtons, guys. Once again, the 0 doesn't really necessarily need to have a value attached to it. So these are some important things to remember, and you want to write them down now because I'm going to clear off the page to give myself some more room. Okay, so here we are back again. Once again, these are ropes up here, here, and this is a weight. Now, let's take a look. What forces are in the y direction? So I'm going to go to a blank page, and I'm going to just look and divide it right down the middle, and on one side I want to make my x direction forces. On the other side I'm going to make my y direction. Once again, this whole side of this page should all add up to 0, and this whole side of this page should all add up to 0. So let's take a look back here. Well, what's going to happen? Well, first, let's look at what forces we have here. Now, we have a force of gravity on point A by this weight that pulls it down. We have an Fg. But at point A, it's stationary. It's at equilibrium, so it doesn't move. It's got some other forces acting on it. It's got a tension that pulls it up this way, and it's also got a tension that pulls it up this way. Call that T1. It doesn't matter, you can call it T. We call this TL, and we call this TR if we wanted to, or left and right. Whatever you want. These subscripts are names that you're making. Now let's give ourselves some values for these ropes, because we're not going to be able to solve anything unless we have a value. So let's go up a little bit, and let's say this rope here, and I'm going to give myself easy values to work with, is the square root of 8. And this length of this rope, this side here, is the square root of 8 as well. That's meters. And the meters is outside the square root sign. Never mind. And then let's say from this point here to that point there, let's say that's a total of, let me see if I can get this right, I think it's going to be 4 meters. So from here to here, we have 4 meters. Now, the next thing to realize is that these forces, TL and TR, they are the two forces that cancel out your Fg. If you were to add all these forces together, they're going to, head to tail, they would add up to 0. Okay, that's great. Now, something to remember, but also from adding up forces, guys, is if you can add up the components as well, and they should add up to your resultant. So in this case, our resultant is 0. When we take these three forces, TL plus TR plus Fg, we should get a resultant. And in this case, our resultant equals 0. Okay, but also remember what we did, guys. We took the x components, the x coordinate at the end of each of these, and we could add those up and get the resultant. And we took the y coordinate of each of these and add those up to 0. So let's take a look at what that's going to be. Back to our document. In the x direction, guys, we take a look. Does this force have a value in the x direction? No, it's only in the y. Does this force? Yes, it does. It's going to have a, what we'll call a TLX, and that's the x coordinate. That's going to be the value up here at that point, or the component vector, whatever you want to consider it as. Both of those are valid ways of defining it. And this way, in the x direction, you're going to have an x component of this. Control Z, get off there, come on. So you're going to have a value in the x direction there. I want to get rid of this. So we have our TR value in the x direction and our TL value in the x direction. And once again, guys, this also, if you think about this, at the point here, you have coordinates, an x and a y. And at this point, you have an x and a y. And what I'm saying is, you found this vector, this TRX, is in fact the x component there. And this TLX is the x component there. Now let's think about y's. I'm making purple. Now both of them have a y value, and the interesting thing is this, and we'll talk about this in a second, but since this is symmetrical, see that these sides are both the same length, you're actually going to get both of them having a, let's move this a little bit out of the way, both of them having an equal, and in the same direction, ty value. So you have a tly and you have a try. Once again, I'm talking about this term right here. This term, the y component, that's the end of your vector, that's your tly. Okay, now what I want to do, guys, I just want to actually just even get rid of this, just so it's not confusing anymore. And we can see we have these values in the x and these values in the y. So when I come over here, I can write, what's in my x direction? Well, FG is in the x direction. TLX, oh, sorry, mistake. Your TLX and your TLY. Oh, geez, Mr. Shaw, just got up, didn't you? Yes. TLX and TRX. Sorry. So once again, when we go back, we look. Here's our two values in the x direction. Geez. Sorry about all those mistakes, guys. What else is in the y direction? Well, the force of gravity that pulls the object down is in the y direction. And then also you have TLY and TRY in the y direction. Now, if you add all these up, and you add all these up, you can get 0. Oh, sorry. So what I like to do is I like to make a formula. It's going to be a very simple looking one. And you're going to say TRX plus TLX equals 0. FG plus TRY plus TLY equals 0. Okay, so you've got these things. Now, where did I come up with this, guys, again? Remember, all your x components can find you the x coordinate of your resultant, and all your y components can find the y coordinate of your resultant, and the resultant here is 0. So if the resultant is at 0, 0, you have a resultant of 0. Okay. Now, let's take a look back at our other sheet. I'm going to clear everything off. I really just want to have a nice clear sheet to look from. Okay, so let's redo one more. Now, the one thing to do next is we're going to make this into a nice looking triangle. Do this and this. Now, we have formulas for our x and y coordinates. Hopefully you remember them. Mr. Lee went over them in class, and we went over them before. I prefer to use the x and y to look like this: tx, or we'll say, be even more specific for today's class, we'll say trx equals tr cosine theta r. Now, basically, what I'm saying is this: here is our right vector, right? And if I have an angle right here, theta r, I can use this formula to find the x component. And we've done this a lot of times in class. So tr y equals tr sine theta r. And once again, the reason I'm really stressing this theta r, it's got to be with respect to the positive x-axis. That's the only way you can do this for this class. And with this formula, we can find those two vectors that we have. When we look back here, I can find my trx and my try using this formula. Well, the trx is not as important, but the try should give us some interesting concepts. Now, how do they give us interesting concepts? Well, the thing we have to realize is that because these vectors, because this is a symmetrical triangle, and when we look at this, we should realize that our y vectors are the same. Because our y vectors are the same for the TL and the TR, when we go back over to the other side, we can treat them as if they're the same. Now, people might be saying, well, Mr. Shaw, why are they the same? How do you know that? Well, if you take a look, this one has this angle here. But if we take a look, actually, let's just look at a different angle for a second. I don't want to take up too much time, but we have two angles here. Now, if both these sides are the same, and then also if this is a right triangle here, which we know that these are going to be rights, then this side has the same length and this side has the same length, and then when we break them into our vectors, this side is going to have the same length for our y component. And it might be just something, guys, for you to try on your own. If you want to do some values, if you want me to show you it, I'll prove it more thoroughly later. I don't want to go over and have to edit this into two parts. So real quick, what I really want to stress, and I don't think I really defined it very well, but is that these two values are the same. So you can treat them as the same. You can go fg plus 2try equals 0, and then you can say try equals negative fg over 2. And I'll leave the remainder for you to figure out, but it's going to be, you're going to have to use your triangle, you're going to have to find the angle, and look at what we did in class. I don't want to use up all my time.